We now discuss Newton's first law of motion. Think of a hockey puck sitting at rest on the ice. Unless someone gives it a push of some sort, it will remain stationary, and if nothing ever interacts with it, it will stay in this stationary state forever. After being struck with a stick, however, the puck will move in a straight line across the rink, with only a slight drag due to friction between it and the ice, which will eventually slow it down and bring it to a complete stop. Suppose, however, it were possible to eliminate all of the friction in the problem, including the friction between the ice and the puck, air resistance, etc. What would happen then? The answer is that it would move in a straight line at a constant speed forever. This is the essence of Newton's first law of motion, which we can formally state as follows. An object continues in a state of rest or in a state of motion at a constant velocity, meaning a constant speed and direction, unless compelled to change that state by a net force. The idea that an object stays at rest indefinitely if not acted upon by some influence, that to which we refer as a net force, is perhaps not so difficult to grasp. However, our everyday experiences may obscure the concepts of Newton's first law when dealing with moving objects. After all, a thrown rock, rolling ball, or coasting bike all eventually come to a halt if we don't constantly propel it somehow. That's because the net force on each of these objects is not zero. The force imbalance in these cases comes from some kind of force of friction. Most people, however, have seen astronauts on the space station throw an object and witness its constant velocity trajectory. A greater net force is required to change the velocity of some objects than others. For example, it's much easier to push a bike than a jetliner. We say the jetliner has a larger inertia than the bike. If we wanted to quantify how much more inertia the jetliner has, we'd have to know the mass of the jetliner compared to that of the bike. In this case, we see that the bike has a mass of 15 kilograms, whereas the jetliner has a mass of 1.2 times 10 to the 5th kilograms. We define inertia as the tendency of an object to remain at rest or in motion at a constant velocity. The mass of an object, measured in kilograms, is a quantitative measure of its inertia. A bit of a warning here. Although they are related, mass and weight are not the same. We now discuss the concept of inertial frame of reference. Imagine riding in a car with a ball sitting on the seat next to you. When the car accelerates or brakes, the ball will move. The ball will also move when the car goes around a corner. In fact, whenever the velocity changes in magnitude or direction, the ball will seem to experience a net force, as will you. Therefore, in the accelerating reference frame of the car, Newton's law of inertia doesn't hold because objects will appear to accelerate or change direction even though no net force is acting upon them. We therefore define an inertial reference frame as one in which Newton's law of inertia is valid. Finally, from this section you should be able to state Newton's first law of motion and define inertia and an inertial frame of reference.